All right, so this is the first example where we're going to actually walk through how we calculate displacements. I know I've said this a bunch, but just like with forces, where a moment I consider a force just a rotational one as opposed to a translational one. When we talk about displacements, we're talking about translational displacements as well as rotational displacements. Right? So here's our structure. It's just a simply supported beam with a distributed load W on it. It's a length L, EI constant. This, it turns out, you may see in a second, to be the simplest problem that we can solve for displacements with. And really what I'm asking now are two things. One is to get the displacement at midspan, right? And the other would be the rotation at the left support, like that, right? So if I were to draw the deformed shape, right, it would look something like that. And this rotation here, right, we would call theta of 0, right? And that's, I'm assuming that I'm going to take x from this side, right? And then this displacement here, right, this we will call v of L over 2, right? So v, again, is the letter that we're using to denote vertical displacement, and the x position for midspan is at L over 2, right? So that's sort of where we are. So the first step in doing this is to, we've got to solve for the moment diagram. Now you do not have to solve for the shear diagram in general, because we're assuming that the shear diagram, or the shear that's on the member, is not contributing to the deformations, right? So what I'm going to do is, just like all the other problems we've solved, I'm going to take a cut. All right. I am going to show my reactions here. And I am taking x from left to right here, right? And my moments I'm applying here is m of x, right? Now you can draw the shear if you want to. We do not have to solve for it, so we're not going to, right? So this is omega, or W, and this is WL over 2. We've solved this problem many times before, right? So if we sum moments about the cut, right, so that's where we always take our moments about. So if I sum moments about the cut equals 0, I am going to get a minus WL over 2, over 2 times x, and I'm going to get a positive Wx, that's the total force, and then x over 2 is the moment arm for the distributed load, right? And then I'm going to get a positive m of x, and then that's going to be equal to 0. And when I solve for this, I am going to get that my moment is WL over 2 times x minus WX squared over 2. I'm going to box that because that is our first step, right? And that, by the way, is good for 0 to L, right? Because there's no other discontinuity in this beam, I don't have to have another x, right? We will do a problem where we have a point load that's a discontinuity, so I'm going to have to calculate the moment diagram piecemeal, one for one half of the beam, one for the other. In this case, this is one of the reasons why simply supported beam with a distributed load is the simplest problem for this. We only have a single moment diagram, and it's valid everywhere. So, moving on, we can now solve for the elastic curve. Or deformed shape, whatever you want to say. Right, so this is now d squared v dx squared, and that equals the moment divided by EI, right? We know what that moment is, so I just plug it in here. WL over 2 times x minus WX squared over 2, like that. And if we want to simplify it, I can pull that W and the 2 out front, and I'm just left with LX minus x squared. I think your book and others typically do this. It's not required, so it's up to you. So then we can integrate it once, and the left-hand side will be dv dx, right? And the right-hand side will be this constant, W over 2EI. Then that first term goes to LX squared over 2, and the second term goes to x cubed over 3, and then I got to add a constant of integration, because every time you integrate, you could have a constant, right? So if I take the derivative of this expression here, right, with the constant, I am going to get that expression there, right? So then we can integrate it again. And now finally we get what we're looking for, which is the elastic curve V of x. So that is W over 2EI. And this is now LX cubed over 6 minus LX fourth over 12. And that is plus C1 times x plus C2. So that is my elastic curve, right? Now, one thing you can notice here is that the elastic curve is fourth order, right? So the highest exponent on x we have is 4. That should make some sense because we took a moment diagram, which was second order, and we integrated it twice, which is going to make it fourth order. So it's always the display shape is always 2 times higher order than the moment diagram. So now we are very close to being done, but not quite done. We now need to solve for integration constants. Using boundary conditions. So I'm going to, so pretty much the entire course, BC is going to be boundary conditions, right? And the boundary conditions have to be, so BC must be in terms of V of x or theta of x, which of course is equal to dv dx evaluated at x, right? So it's either the boundary condition can be a slope, the boundary condition could be a vertical displacement, right? The boundary condition cannot be, in this formulation, 0 moment, for example, right? You will see later on that there's sort of a way to do that, but not here. So our boundary conditions, hopefully you can see these, are that the V of 0 is 0, so at the left-hand side of the beam there's no deflection, and V of L is also 0. So at the right-hand part of the beam, where there's a roller support, there's also no deflection, right? So if I substitute in the first boundary condition, right, I'm going to get W over 2EI. This is L times 0 cubed over 6 plus 0 to the 4th over 12 plus C1 times 0 plus C2 has to equal 0. And from this, we get that C2 must equal 0. So that's my first constant of integration. And then the second constant of integration here will be that v of L. And by the way, if you have constant of integration that equals 0 and it evaluated at, say, x equals 0, that's where you want to start, because you'll see everything cancels out just like it did in the previous one. And it makes the second boundary condition a lot easier to solve for. So this is w over 2ei. This is now L times L cubed over 6 minus L to the 4th over 12 plus C1 times L equals 0. And when you solve for this, you will get that C1 is minus L cubed over 24 EI. Just like that. So now we can write our final equation, right, for the elastic curve. So v of x is now W24 over EI times 2LX cubed minus LX minus x to the 4th. So all I did was plug in, and then I pulled out the constants. Right? So we can solve for midspan deflection. So that's v of L over 2. So I'm just going to plug in L over 2 for x. So this is 2 times L cubed minus L. Oh, what did I do here? So this is L cubed like that. That's what I forgot. And this guy is L. Let me erase this, sorry. Trying to go too quickly. So this is L over 2 cubed minus L cubed times L over 2 minus L over 2 to the 4th power. And when you solve for this guy, we end up with minus 5WL to the 4th over 384 EI. So that may be the first time that you see that number or expression, 5WL to the 4th over 384 EI. It will not be the last, right? This is a very common displacement. Again, it's the displacement of a uniform beam with a, or a simply supported beam with a uniform load on it, so it sort of pops up all the time. Whether you want to or not, you probably will end up memorizing this because it does, pop up so much. So then on the last one here, we've got to now solve for the rotation at x equals 0, which is the left-hand support. So in order to do that, the first thing I need to do is solve for not the vertical displacement as a function of x, but the rotation as a function of x. So I just take the derivative of v of x. Right? And when I do that, this is going to be 24 EI. So the first term becomes 6L x squared. The second term becomes minus L cubed, and the last term becomes minus 4x cubed. I can then plug 0 into this. Right? So this is theta of 0 is just 24 EI. This is now 6 times L times 0 squared minus L cubed minus 4 times 0 cubed. And this turns out to be minus WL cubed over 24 EI. Right, so let me box that guy. We'll put a star next to it. So that is the displacement, rotation, sorry, of the left-hand support. If you notice the negative there, right? So this is going to be very similar, not similar, it is, you know, our universal sign convention. So that's X and Y, and that is Z. Z is the right-hand rule, right? And so in this case, because it's negative, it's going to rotate in that direction, right? In this case, it's negative, so that means it is going to deform downward, right? So that's our rotation at the left-hand support. This is our displacement at midspan. And if we go back to the original problem, you can see, okay, the rotation on the left-hand support, it is in the clockwise direction. That's what we would expect, which is negative from a right-hand rule standpoint. And the displacement at the middle of the beam is downward, right, which is also sort of expected. All right, so if there are any questions, you can bring